Dear all, good morning. Our lecture is Nature of Quadratic Form. In this lecture, we are going to discuss what is the nature of a quadratic form, that's index, signature, and rank. Now, already we discussed what is the quadratic form, and last class we discussed reduction of a quadratic form to canonical form by orthogonal transformation. Using the canonical form, we can classify the quadratic form. That is, we can find the nature of quadratic form. Now we'll see. First of congruent matrices. When we say two matrices are congruent, the definition: symmetric matrices A and B are called congruent. If there exists an orthogonal matrix Q, that A equal to Q transpose BQ, or you can write B equal to Q transpose AQ, whatever. Same as the similar matrices. But here we are symmetric means we are getting orthogonal matrix. Every orthogonal matrix is the non-singular non-singular matrix. Q naught equal to Q naught. Always invertible. Then similarly there exists some invertible matrix, orthogonal matrix. For symmetric matrix, there exists some orthogonal matrix. This is the one. If we write it has A approximately equal to B. That's the notation. Congruent to B. Example: matrices A and B are congruent. Matrices are congruent. That means you can write A equal to there exists Q transpose BQ, or B equal to Q transpose AQ. Now inertia. What is the inertia? The definition of inertia: the inertia of a real symmetric matrix. The inertia we can find in the symmetric matrix. That means all the eigenvals are real. Is defined to be the rho nu zeta, which what is the rho nu zeta? The rho is respect to number of positive eigenvalues, nu is respect to negative eigenvalues, and zeta is the zero eigenvalues. Counting algebraic multiplicity. Suppose positive value is repeating 3 times, to count that 3 times, not only one time. For example, let A be a 4 by 4 matrix whose eigenvalues are or lambda equal to, suppose 2 1 comma 2 minus 2 0, suppose. Therefore inertia of A is, so the inertia means rho nu zeta equal to, rho means number of positive eigenvalues. How many positive eigenvalues? 2. Nu, number of negative values. How many negative values? Only one. That is 1. Number of 0 0. Suppose lambda equal to, let's see, eigenvalue 2 2 1 minus 1 0. In that case inertia is same, 2 1 0. Suppose I get minus 1 minus 2. In this inertia, for this case inertia is equal to number of positive 1 2 2, number of negative 2, number of 0 eigenvalues 0. There is no, that means 2 to 0. Inertia means number of positive eigenvalues, negative eigenvalues, and 0 eigenvalues. You have to counting the algebraic multiplicity. If it's a positive eigenvalue repeated 3 times, the positive eigenvalues are, if repeating 1 time, only 1. If repeating 2 times, I will take 2. Now, Sylvester's law of inertia. By using the Sylvester law of inertia, you can say congruent matrices. Yeah, this statement, Sylvester's law of inertia, states that A approximately equal to B. That means A congruent to B. If and only if A and B have same inertia. If A and B have same inertia, you can say they are congruent. Same inertia means that not same eigenvalues. They have same number of positive eigenvalues, negative eigenvalues, and 0 eigenvalues. Number of definitions index. The number of positive terms in a canonical form of the quadratic form is called the index of the quadratic form. The number of positive terms in a canonical form, the quadratic form is called the index of the quadratic form. So it's a quadratic form like this one. X square minus 3y square plus 4z square. It's a quadratic form. It's variable in it's a canonical form. There is no cross term. That means canonical term. See, the index of canonical form same as the index of the quadratic form. What the index? Index of this one? Index means number of positive terms in the canonical form. How many positive terms? 1, 2. The index is like this one. Signature. The number of positive terms minus the number of negative terms in a canonical form is called the signature of the quadratic form. That is the signature of the quadratic form. Signature. Signature means difference between the number of positive terms and the negative terms. So it's a signature of above the signature is for this quadratic equation. Number of positive terms minus negative. Number of positive is number of negative is 1. 2 minus 1 is 1. Now, if R be the rank of a quadratic form, that means number of non-zero terms in a canonical form. The number of non-zero canonical terms. If 3 terms, the rank is 3. If only 2 terms, non-zero terms, rank is 2. Only 1 term, rank is 1. Now, P be the index and S as the signature. Then S equal to R minus P or R equal to signature plus index. This is the one. Or you can say R also the number of rank or the number of non-zero eigenvalues because now here observe here when we are writing when we are converting quadratic form to canonical form, we are getting these coefficients x square y square z square coefficients are eigenvalues of that matrix. The rank is same as the number of non-zero eigenvalues. If a 3 by 3 matrix, we get 4 non-zero eigenvalues. Non-zero. One is zero eigenvalue. The rank is only not one is zero eigenvalue is there. Rank is it's a singular matrix. That means rank is 2. The rank means number of non-zero eigenvalues. Now two symmetric matrices A and B are congruent if and only if the canonical form of A and B has the same rank, index and signature. These all are same. Rank, index, signature. Both are same. If it's a inertia is same, it's a congruent, or rank, index, signature are same, you can say A and B are congruent. This. Now, what is the nature of quadratic form? In the quadratic form Q of x, the x transpose Ax in n variables is said to be positive definite. So invariable means A is n by n matrix. We know we get n by n matrix. It's positive definite. That means positive definite means we know all the eigenvalues are positive. Already we know this one. Now for this quadratic form, the rank must be n, and the index means number of positive terms in a canonical form must be n. If R is n and P is n, it says it's a positive definite. Or if all the eigenvalues of A are positive. In this case, the matrix is positive definite. The negative definite. If R is n, the rank is matrix. And P is 0. That means number of positive terms in a canonical form is 0. Or if all the eigenvalues of A are negative. In this case also negative definite. Now positive semi-definite or semi-positive definite. If rank is less than n, that means rank is not full matrix, less than n. Less than n means at least one eigenvalue is 0. And index is R. Index is R. That means if all the eigenvalues of A is greater than or equal to 0 and at least one eigenvalue is 0. At least one eigenvalue is 0, the matrix is called positive semi-definite. The quadratic form is called semi-positive definite or positive semi-definite. The quadratic form. Now negative semi-definite. When we say a quadratic form is negative semi-definite, if rank is less than n, that means in the quadratic form number of non-zero terms are less than n and index is 0. That means there is no positive terms in canonical form. That is in that case negative semi-definite, the quadratic form. or the matrix if all the eigenvalues of less than or equal to 0, that means all eigenvalues are negative, at least one eigenvalue is 0. In that case also we can say negative semi-definite. Now indefinite. If all other cases, not this above cases, all other cases, or if A has positive as well as negative eigenvalues, that means club of positive and negative, in that case also we can say the quadratic form is indefinite. So already we discussed this quadratic form. P of x is 3x square plus 2y square plus 3z square minus 2xy minus 2yz. This one we are converted to this one canonical form. For the canonical, last class we discussed canonical form is y1 square plus 3y2 square plus 4y3 square. This is a canonical form. This one. This the matrix of this one is the, this matrix is 3 minus 1 0 minus 1 2 minus 1 0 minus 1 3. This is the one. Already the eigenvalues of this matrix is A is 1 2 1 3 4. And by using this one concept, eigenvalues of A are all are positive, therefore it is positive definite. The matrix is positive definite. If matrix is positive definite means the quadratic form also positive definite. This also we can classify that one. Or converting canonical form. Now see this one. What the rank? Rank is number of positive terms in a canonical form. Three forms are there. This rank is 3. And what the index? Rank is 3. What the index? Index also 3. Rank and index both are same. Then the matrix is positive definite. Rank and index is same. Positive definite. And signature, what the signature is 0. This is applicable in the quadratic form. All terms must be there. So this one is this one. This is not, we are getting rank. We know rank is equal to s plus p, signature plus index. But it's not. The canonical form contains all all variables. Suppose you are taking this one. Already we discussed this one. X1 square plus x2 square plus x3 square. Okay, sorry. Okay, we'll discuss later this one. Now see this example. Determine which of the following matrices are congruent to each other. The congruent to each other we can go for inertia case. One in previously one more case is that congruent matrices. Matrices is inertia. Congruent quadratic forms you have to go for rank, index, and signature. You now find the eigenvalues of each one. Yeah, the eigenvalues of A are this one, B 0, 5 plus or minus root 33 divided by 2. And C is 1, 1 plus or minus root 5. See that inertia. The rho means number of positive eigenvalues. How many positive eigenvalues? Positive and root 6 positive. Negative eigenvalues only minus root 6 1. Zero eigenvalues is 0. In this one, what the positive eigenvalue? Only 5 plus root 33 divided by 2. Only 1. Negative 5 minus root 33 negative. That's 1. Zero eigenvalue also 1. In this one, positive 1 and 1 plus root 5 2. Negative is 1. Zero eigenvalue 0. Now here observe here the matrices A and B have same inertia. Same inertia. Therefore, A is congruent to C. By By eigenvalues, we can say the matrices are congruent or not. Have same number of positive eigenvalues, negative eigenvalues, and zero eigenvalues. Then we can say they are congruent by inertia. Inertia. We know this one rank equal to S plus P, signature and index. This is applicable. It's possible. It's possible when the canonical form contains all variables of quadratic form. Quadratic, quadratic form. For example, just last class we discussed the quadratic form. Q of x is x1 square, x2 square, x3 square. Now this is a 2x1, x2, 2 x2, x3, plus 2 x1, x3. This one. And this matrix is 1, 1, 1, 1, 1, 1, 1, 1, 1. What are the eigenvalues? Eigenvalues lambda equal to 0, 0. Now what is the inertia? Inertia you can write this one. Rho mu zeta equal to number of positive 1, number of negative 0, number of zero eigenvalues 2, 1, 0, 2. Inertia. Now this canonical form. What is the canonical form? Canonical form Q of phi equal to what we are getting canonical form? Y1 square, or you can write 3y3 square. So your right eigenvalue is first or last. Now observe here in this one. What is the index? 1. What the rank is? Number of positive, number of non-zero eigenvalues, number of non-zero terms 1. And signature positive minus negative. Positive negative there is 1. But are not equal to S plus P, because here it contain only one term. Correct term is not containing terms. This is applicable when the canonical form has total variables. Total, if it's a 3 variable term, the quadratic form has 3 variables, the canonical form must be 3 terms. 4 variable, 4 terms. That means quadratic form contain terms number of variables. 3 variables, it's contain 3 terms. Variable must be contain 4 variables. In that case, R equal to S plus P. We can classify by using the eigenvalues also. Okay, for example, identify nature of the quadratic form. Nature of quadratic form: x1 square 4x2 square plus x3 square minus 4x1 x2 plus x3 x2 minus 4x2 x3. And the nature of the quadratic form. Nature means you have to check is positive definite or negative definite or positive semi-definite or negative semi-definite or indefinite. That's the nature. Now the mathematics, or not only symmetric, whatever you write, the matrix. Generally, we are getting symmetric matrix. The associated expanding matrix of given quadratic form is A equal to, suppose, 1 x1 x2 minus 2 x1 x3 is there. So this one x2 x3 x2 we are writing x1 x2 at x3 x1. Yeah, x3 x1 x3 x1 this is minus 1, this is minus 2 x4 x2 x3 it's minus 2 minus 2 1. This is the matrix. Now find this eigenvalue. The eigenvalues of AR already you know how to find eigenvalues. The eigenvalues of AR we get 0 0 6. Now this matrix has two, the A has two 0 eigenvalues and one 2 eigenvalue. Yeah, there. Yeah, you know at least all are, that means all are positive. At least one eigenvalue is 0 eigenvalue. It is positive semi-definite. Yeah, two eigenvalues are 0, one are positive. Therefore, A is positive semi-definite. Semi-definite. Matrix is positive semi-definite. What is the rank of this one? What is the rank of A equal to? Rank of A is number of eigenvalues, number of non-zero eigenvalues. How many non-zero eigenvalues? Only one. The rank is 1. You can check it. You can find this rank is 1. Now generally we get canonical form. It's converted to the coefficient of eigenvalues. If asking what the index, we will get 1. Index also we get index of quadratic form is 1. Signature also 1, but it's not satisfied that rank equal to signature plus index, but because the canonical form it's contain only one zero term, one non-zero term. This is the rank. What about inertia? Inertia of A is split. Directly can row. Number of positive 1, number of negative 0, number of 0 is this 1 0. This is the 1. So this is the procedure to find nature of the matrix. By nature of the quadratic form, we can go for eigenvalues and eigenvalues, or that you can go for that index and rank. If rank, you can go for this method. Anyway, you can go for eigenvalues or you can use this one. Positive and negative definite. This one. If it's not one of these 4 cases, then it's indefinite. So we go for eigenvalues. If it has above positive and negative, the matrix is indefinite. This is the one. Nature also we can, the index also we can find generally quadratic form, in the canonical form. Is suppose let lambda 1, lambda 2, lambda 3 or be eigenvalues of A of quadratic with quadratic form is quadratic form x transpose Ax. Suppose the canonical form will get, the canonical form of this one we get lambda 1 y1 square plus lambda 2 y2 square plus lambda 3 y3 square by orthogonal, this orthogonal transformation. By orthogonal transformation we are getting this canonical form. If you are using a different method, it's not get this canonical form with eigenvalues. By orthogonal transformation we will get this one x equal to qy. By orthogonal transformation only, the canonical form, the variable coefficients are eigenvalues. Variable coefficient are eigenvalues. If you know eigenvalues, we can find the index. This one, we can find index. Index is the number of positive eigenvalues. The canonical form has total terms, total variables. Yeah, S is the signature. Signature is the difference between and negative eigenvalues. Negative eigenvalues. And rank. This index, signature. This is the rank. Rank is the number of non-zero eigenvalues. Eigenvalues. It's also correct. Now I am stop here. Thank you.